Okay, so I'll try to start sharing screen. Let me find it. This should be the right thing to do. So it seems that somebody has started recording. I don't think it was me. Is it? Did somebody started recording or not?
Shall I speak? Sorry, it was me, but I just randomly click on that button. I saw the recording button in the previous presentation, so that's why I did it. So my apologies.
No problem.
I can start it right now.
Yeah. No, do not press it. It was just first thing that I wanted to ask you because we have some students from abroad who cannot be present physically because they are in different time zone, and for those people we will record all the lectures. So this is just that I am saying that to you, that we will be recording those lectures, and everybody shall know about that. And those lectures will be available afterwards, after the lecture finishes. Okay, so just to confirm, do you see my screen, the slides?
Yes.
Perfect. Yes. Yeah, good. So you have noticed that I have started talking in English. That's because of those foreign students. I hope that everybody is okay with that. If somebody has some problems with that, then just let me know, and we will try to solve it somehow. But I don't think we will solve it by switching to Czech language. Maybe this is going to be recorded, so if you don't understand everything, maybe you can just listen once again and maybe slowly and do some pauses in between, and it should be okay, like to understand them. Okay, anybody has problem? Everybody understands? Or maybe I will switch to Czech for a while. Takže česky, souhlasíte nebo nemáte někdo závažný problém s tím, že to bude v angličtině a přednášky teda, že budou v angličtině? Pokud máte někdo problém, tak zvedněte ruku, ať to vidím.
Může jenom mít dotaz.
Určitě.
Já mám zapsanou českou verzi toho předmětu, ale máme na OI povinnost absolvovat jeden předmět v angličtině, takže jestli by nebyl problém zapsat si tu anglickou, a když stejně se bude učit v angličtině.
No, můžete, dokonce si nejsem jistý, jestli je potřeba si zapisovat tu anglickou, tam byste pak měl možná nějaký opletačky s kapacitama, s takovýhlema věcma. Vím, že už jsem to v předchozích letech prostě dělal, že jsem někam jenom musel napsat, předmět byl učen v angličtině a tím pádem se tomuhle studentovi může uznat jako anglický. Takže možná to ani nebude potřeba, dá se to takhle uznat.
Dobře, díky.
Tak jo. So switching back to English, welcome in new semester, and welcome at this course which is called Real-Time Systems Programming. This is an introductory lecture, and I will briefly tell you about what this course is about and how we will organize it and so on. It might be a bit more difficult this year because of this distance learning. One specialty of this course is that in labs you will work with hardware. So we have to give you remote access to that hardware, which is a bit tricky, but I think we will manage it. So you should be able to do everything as normally. So what is this course about? Real-time system. So today we will talk about a bit what is a real-time system, and in general, real-time system is an abstract term. A real-time system can be both hardware, software, can be even something else. So in our case, we will be talking mostly about software, real-time software, but the techniques and methods that we will talk about at lectures apply even to other domains, like maybe computer networks, like hardware design, and even something else. So real time, and I will repeat this several times during the course, and I want you to remember that real time is not about something being fast, but real time is about something being deterministic or predictable. It can be a bit slow, but it can be slow all the same, all the time the same slow. Yeah, so it's predictable. Then one part of the lectures, or maybe the second part of the lecture, we will cover a few principles and theory of real-time systems. How mostly we will be interested in analyzing the temporal properties of the system. So temporal properties, like it means like will everything be computed in time, or there will be some delay that we don't want to be there. So this is the analysis, and this is the difference between let's say normal software and real-time system. Normal software, you run it and it runs, and maybe users complain that it is slow, but okay, you click somewhere and it's slow, so the user just waits, and that's it. But in real-time software which is controlling an airplane or something like that, if the system is randomly slow, maybe the airplane crashes. So this is the difference between real-time software and non-real-time software. Theory about real-time systems and the analysis of real-time systems will be the part of the second part of the lectures. In the first part, we will talk mostly about more practical things. This is what you will need for your labs, for your practical classes, and we will look at mostly at VxWorks operating system. VxWorks is one operating system used in real-time applications. It's not the only one. There are many others that can be used there. For example, nowadays even Linux can be used well. But we will talk mostly about VxWorks, but I will also mention how are things in Linux when compared to VxWorks. So I will talk about that later. Okay, and the last part of the lectures will be devoted to safety critical systems. The reason is that in many cases, when you are developing a real-time system, it is also a safety critical system, meaning that if there is some problem in that real-time system, it can cost human lives or something like that. If the airplane crashes because of software malfunction, it's a problem. And safety is difficult, not because it's like something very complex, but it's difficult because the systems that are being built are complex. And I think it's important for you students to be exposed to safety problems as early as possible. because it takes some years before you get familiar with the concept and before you can develop, let's say, safe systems. So we will have 2 lectures about safety. If you are interested in this course, and then there is some literature. Mostly you won't need this literature to pass the exam, to pass the course, but from time to time I will refer to those books, like if you are interested in more details and so on. So just look at those books. You can borrow those books in the school library, if I'm not mistaken. And I think that this book is also available from our website in some form. Okay, so this is what is this course about. By the way, if you have just any question, just maybe raise your hand. Maybe I miss when somebody raises your hand, so just switch on your microphone and just ask the question. Feel free to interrupt me if people are not interrupting me every minute. It's okay to interrupt me. Okay, so this is what this course is about. Then what it is not about. A few years back, real-time web was a buzzword. It's not a buzzword nowadays, but it's not about real-time web. It's about more fundamental principles, and it's more about like low-level programming, embedded systems, and so on. So here is the list of lectures. I apologize. Maybe the order of the lectures will be different this year, but it's mostly what I have already told you on the previous slide. So this is today we will start with the introduction, and maybe we will have time to start with the VxWorks operating system. The thing that you are probably interested in is about the grading and what are your duties, what you have to fulfill to pass this course. So it's quite simple. It's summarized on this slide. Basically, we have exercises or labs, and we have lectures. So from the labs, there are at the beginning, and we will talk in more detail about that. There are 7 smaller tasks that are like going from simple to more advanced things, and you will learn how to work with the VxWorks operating system and how to do some real-time stuff or low-level hardware-related stuff there. And then at the end of the term, there is a bigger semestral work where you should like use the knowledge that you gained from the small from the tasks at the beginning of the term. So you get the points from both tasks. Like every task has some number of points. There are penalties for late submission and so on. And then there is this semestral work. Also get some points from that. Finally, there is an exam at the end. There is a written test. You have to get at least 13 points from that out of 30. If you have less points, then you have to repeat the test. Then there is not mandatory but voluntary oral exam where you can get some extra points to get a better grade, and the grading is like standard grading from the university. So that's the like what you need to do to pass the course. Then about the communication, this is a bit outdated. I forgot to update this slide, but what's most important is this. Oh, sorry, you didn't see my cursor. Is this web address? So please remember it. There should be there should be links to this web address from other websites, like from Moodle. If you find this course on the Moodle, there is just this link to this address, and everything related to this course is there. Then there is my email. You can write me an email if you want, but there is no mailing list for today. There is, I'm crossing this. This is not, actually the mailing list I think still exists, but do not subscribe there. For this year, we will communicate primarily over Teams. So if you have a question or something like that, just write to the Teams. I think I will create some more channels after the lecture, like for the labs, for the lectures, for questions, and so on. So just write there. I think it will be quite natural both to write there. And if you write to wrong channel, nobody cares. Just maybe we will tell you, please write to another channel, and so on. So Teams is the primary means of communication. And we will also have lectures and exercises over Teams if it works well. Let's see. Last semester it works quite well. So if it works well, we will be using that. Okay. So are there any questions to the organization of the course? No, perfect. So we can start talking about real-time systems and about some introduction. So I have already told you briefly what is a real-time system. So I am repeating it again here, and I will repeat it all over all the lectures, I think. So real-time system is a system whose specification includes both logical and temporal correctness requirements. It's like difficult. It's difficult. And now I just noticed that there is some chat. Yeah, okay. So nothing interesting in chat. Yeah, so what does that mean? So logical correctness, if you have ever programmed anything, then probably you cared about logical correctness. You wanted your program to do what you wanted it to do. Like if the program has to sum two numbers, the result has to be correct, and so on. But in real-time systems, we also care about temporal correctness. Temporal means like time-related stuff. So basically, it means that if we compute some results, deliver some results somewhere, we have to deliver those results at the right time. Typically, at the right time means like within a deadline. So the deadline is a key term in real-time systems, and we don't care if the results are delivered before the deadline, but usually it's problem if the results are delivered after the deadline, and we perform some kind of analysis. Here you can see it's like a worst case analysis where we try to ensure that everything finishes before the deadline. There are different definitions of real-time systems. So for example, a real-time system can react in deterministic ways to unpredictable events is another possible definition. And I'm sure you can find other definitions. But the temporal aspect is the most important one. And yeah, so I have already mentioned that what you have to do in addition to programming like a logically correct system, you have to analyze temporal properties of a real-time system. And typically this means ensuring that everything finishes before the deadline. But maybe you can ask like, okay, so what is the deadline? So is the deadline like 1 second or 1 millisecond or 1 month? what is the deadline? And the answer is, it's hard to say. It's application dependent, it's system dependent, it depends on many things. So in this course, we will not talk much about like what is the correct deadline for such a system, because this follows maybe it's not a like software engineering topic. It goes from like maybe physics. It depends on physical properties of the things around us. It goes from legislation. It goes from, I don't know, maybe some chemical. If you do something, if you are controlling some chemical processes, it goes from chemical properties. So you need to be like domain expert to derive what those deadlines are or temporal requirements are. But once you have the temporal requirements, then we can do something with that, and we can design our systems, our software to fulfill those temporal requirements. So typically, real-time systems have some common characteristics. I'm not saying that every real-time system has all those characteristics here, but it's like typical. Quite often you see those characteristics. So let's go briefly through it. In many cases, real-time systems are event-driven, or some people call them reactive. It means that the system reacts to the events which go from outside of the system, and typically has to react on those events within the deadline. Yeah. Another typical property is that misbehave or failure is often expensive, dangerous, or life or environment threatening. This relates to what I have already told you. It's the safety critical aspect of many real-time systems. In many cases, parallel or multi-threaded programming is employed. You will see why on the next slide or a few slides from now. Typically, continuous operation without human intervention or supervision is required. Maybe now is the time to show you some example. So I stop sharing. Do you see still my slides or not?
No.
Oh, okay. And do you see me full screen on the webcam?
Yes.
Yeah, that's perfect. So I have some. Normally, if we have normal lecture, I would take this and pass it to you to look at. So this is a typical like real-time system that you can meet in many domains. So this is a control computer from a train. This is somewhere inside some machine or somewhere, and it controls the train. And there is a CPU board, like maybe this one. It's a bit older hardware, but it's a CPU board, and there are some communication links and so on. But the key characteristics is that there is no display, there is no touch screen, there is no keyboard, mouse, anything. If you want to connect to this computer, you just connect with serial line over here, and this is how you interact with this computer. And this is just an embedded system with some real-time properties. So for me, this course is mostly about such a system, of course, and you will see shortly there are different kinds of real-time systems where, for example, multimedia applications where you have displays and keyboards and everything. But this course is not only about real-time systems, but it's also about embedded systems development. And this is like what I consider embedded system. Embedded system, one definition of embedded system is like a system which is system which is completely embedded into technology in control. So this kind of computer is embedded in the train, and it controls the train. And you can find a similar systems in airplanes, in cars, and who know where else. So let's switch back to screen sharing. Now, do you see my slides again?
Yes.
Perfect. So continuous operation without human interaction, strict demands on reliability, fault tolerance, and so on. Again, imagine train control and so on. And predictable behavior. You basically want your airplane to behave predictably and not crash. So let's look at some typical examples. So I have already mentioned few typical example is some kind of maybe car. This is a car. And nowadays, if you have like a high-class car, it's not uncommon that a high-class car contains like 70 computers inside, and each computer, each electronic control unit controls some aspect of the car, like engine control and suspension control, and I don't know, whatever. And many of those systems have real-time or temporal constraints. So in automotive, you will find many real-time systems. Another typical application, space program. This is I don't remember which, but some Mars rover which is going on Mars, or was going. And an interesting thing is that the VxWorks operating system that we will or you will work with at this course is running on most, if not all, the rovers that were sent by NASA to Mars. So VxWorks is that kind of operating system which is like reliable, trusted, and so on. And people are sending it to Mars to control those rovers, for example. And another example, again, I have already mentioned that typically all the multimedia systems are also real-time systems. For example, if you do something with audio, you may know that whenever there is one audio sample missing, human ear can immediately hear that there is some problem with the sound, and you immediately hear something which doesn't belong to the sound. And such a problem is typically if your software is late, if the software delivers the sound to be played a bit late, then you see the gap, and it's not very pleasant to hear. So multimedia systems are also real-time systems. We will talk about other examples later. I think this is sufficient for the interaction. Now we will look at some misconceptions that people have about real-time systems. So this is quite old stuff. John Stankovic wrote a paper in 1988 and wrote about misconceptions that people have about real-time systems. So to be honest, some of those misconceptions is no longer a misconception today, but still there are few misconceptions that even people today do not really understand, or they think it is about something else. So let's briefly go through that and let's have some comments. So there is no science in real-time system design. Yes, if the real-time system is really simple, then there is no science, but during this course we will see that there is some space for science or theory of operation and some methods or scientific methods that are handy. Another, and this is still common. Every year I meet few people who think like this, that advances in computer hardware will solve all real-time requirements for us. So it's not true. It's true for some problems and some problems, but in principle, if you design your system in an incorrect way, no hardware can save you. If it is wrong from real-time system perspective, you can have as fast hardware as you can, and it will be still wrong. So hardware is important, but it does not solve everything. Real-time computing is equivalent of fast computing. Yeah, so this is another very common misconception even today. And remember, repeating today for the third time, real-time is not about being fast, but about being deterministic. It means it can be deterministically fast, but real-time is even if it is slow, but deterministic. What is not real-time about is that in 90% of cases it's fast, and in 10% cases it's slow. This is not what we want. If it is slow, we want it to be slow all the same time, or all the time, or we just want to say in 100% of cases the results will be delivered within 1 second, let's say. And maybe 1 second is slow for somebody, but for some applications 1 second is perfectly okay. And so then we can say this is real time as well. If for somebody needs 10 milliseconds to have the results in 10 milliseconds, then it's also real time, but being fast is not the key property of real time. Yeah, so it's written here. Real-time programming is coding in assembly. So okay, this was maybe true in 1998, but probably today very little people actually program something in assembly. So let's skip that. Real-time system research is performance engineering. It's more or less the same. For real-time, we care about deterministic performance. Typically, performance engineers, they care about average performance. So typically what you hear today, there is some, I don't know, performance department at Amazon, and they care about how many requests per second they serve, their web servers serve, or their whatever servers serve. And they say like, oh, we have 1 billion requests per second, but they in many cases they do not say, and every of those requests will be served within 10 milliseconds. They talk about average performance, which means that maybe most of the requests will be served below 10 milliseconds, but maybe there are some requests that will take 1 second to be finished. And most performance engineers do not care about those outliers, let's say. They care about this average stuff. The problems of real-time systems design have been solved in other areas. Yeah, so again, other IT areas typically care about average performance. We at real-time, we care about worst case performance. It is not meaningful to talk about guaranteeing real-time performance because there is no bug-free software and 100% reliable software. So yes, this is true. Anything can break, but of course we don't want our software to be the weakest point. So and that's it. Real-time systems operate in a static environment. Many real-time systems are simple and operate in a static environment, but there are even systems that operate in dynamic environment, meaning dynamic environment like these things are changing. Like we have, I don't know, different number of clients connecting, we have different network capacity available and so on. So there are techniques for real-time systems, even how to handle such a dynamic aspect, and we will also talk about that in this course. So now, just to clarify what is a real-time system even more, there is a question for you. So is a payroll processing system a real-time system, meaning that if you work somewhere, every month you have to get you get money, and you get like a paper saying, oh, we gave you this amount of money and this amount of insurance and this amount of taxes and so on. So there is a clear deadline. Every month we have to print, or somebody has to print the bill. So what do you think? If you think that this is a real-time system, please raise your hand. And now I have to switch to the list of people here. Okay. So somehow. Yeah, some people, like 18 people, think that it is a real-time system, or maybe even more. It seems like it is automatically. Your hands are automatically going down. So some people think it is a real-time system. Some people don't think it is a real-time system. So yes, according to strict definition that we have been talking about, it is a real-time system. There is a clear timing constraint once every month, maybe first day in month it has to be printed. But most people do not consider such a system as a real-time system. So the thing how we look at systems and whether they are real-time systems or not is that we are mostly interested in systems where it is not by default known how to meet the timing requirements. Here, for those payrolls, almost whatever you do, you will be able to finish printing of those payrolls by the deadline, because it's easy. You need really to do something bad or screw it up seriously that you won't be able to fulfill this deadline. But every sane person can do it within the deadline. And we are interested in systems where it is like challenging to fulfill the deadlines. And to think about that, or which are those systems where it is challenging? It's all about resources that we have available for solving the problem. And by resources, we typically mean like computing resources like CPU, memory, network, and whatever. And if the system is such where there is enough resources, we say that the resources are abundant, then it means that whatever we do, we will meet the deadline. And this is exactly the case of the payroll processing system. This is not very interesting for us. On the other hand, there are systems where simply the resources are insufficient. Whatever you do, you won't be able to do it within the required timing constraints. Today's technology is too slow. The performance is slow for this kind of problems. And then there is a class of problems where we say the resources are sufficient but scarce. And this is what we are interested in this course, that you can meet the deadlines if you carefully use your resources and carefully design your systems. And of course, this class of problems changes over time. For example, remote login to a computer and interactive work with remote computer was like a problem where the resources were not sufficient in 1970 or something like that, because everything was too slow and so on. But nowadays we are having lecture with video stream and screen sharing and everything, and the video is delivered in real time. Sound is also being delivered in real time. Hopefully you don't hear any gaps in the sound or glitches or whatever. So interactive video, we are somewhere here, and interactive video is no longer a problem today. But still, there are some problems that were impossible in the past, but nowadays we can solve them with some clever design. So these are the applications that we are interested in. So now let's look at some more examples, like more technical examples of real-time systems. I think that most of the people in this course are from cybernetics and robotics study program, and this is a typical system that people from cybernetics and robotics deal with. So it is a control system, and control system has some input. Typically there are some sensors. Those sensors measure some quantity, like position of whatever. This quantity is converted to the computer with AD converter, and then there is some control action computation, like PID controller and LQ controller and MPC controller, whatever controller. The controller produces some value. The control action value, and again this value is converted to the physical world, to some voltage, current, whatever, and it controls some system. So, and the system, for example, motor, we will at the labs we will be controlling the motor. So you can imagine such a system as being real-time system, because somebody is asking something, or what is this? Network is problematic part of remote desktop, in my opinion. Yes, could be, but even for networks, there are special real-time networks. So if you have a network which is not designed for real-time traffic, then of course network is problematic. But for example, in automotive, you have real-time networks. In aeroplanes, there are real-time networks which are specially designed for real-time systems. And nowadays, with 5G and so on, this real-time networking also goes to like normal networking. So this real-time is merging the normal networks, but in the past, the networks were not like typically were not, or let's say consumer computers networks were not designed for a real-time operation, but this is changing nowadays. Yeah, so let's go back to the slides. So every control system is typically a real-time system because every controller has some sampling period, and this means that every, for example, millisecond you sample new value, you have to compute a control action and you have to apply the result. If you are with the computation or whatever happens here, if you are too late, maybe you cannot control the system. If the system you are controlling is a car or airplane, maybe it can crash. And this is a problem. So every control system is a real-time system. So this is, I think, what I have already said. And then there is an example like how such a control system can look like. So typically, a control system is not like, couldn't be as simple as this simple. There is one control loop, like every millisecond you do this. There could be like a hierarchical control system or multi-level control systems. For example, that basically there are multiple control loops. One control loop runs, for example, 180 times per second. Then there is a slower control loop, like 90 times per second, and even more slower one, 30 times per loop. So this is another control system, like helicopter control system. But talking about multi-rate or multi-level control systems, things can be even more complex. Typical situation in aerospace industry. So you have an airplane, and this airplane is controlled by onboard control system. So it measures various quantities like air speed, altitude, I don't know, whatever, and there is a control system, control computer inside the airplane, which controls the airplane. So, and this is the classical control system, classical control loop that we have just been talking about. But on top of that, there is another loop, and there is like navigation loop. So this low-level control loop, this controls like that the wings are properly in the proper angle, and all those mechanical stuff in the airplane are properly controlled at proper position and so on. And then there is typically this works like every millisecond or every few milliseconds. This is the sampling time of this control system. Then there is a navigation system. The plane follows the trajectory. The plane follows the trajectory that is planned by some air traffic control and so on. So this is the autopilot. You just press the button, like keep this altitude and keep this course and so on, and the airplane follows the path. Maybe it can change the course automatically and so on. This is not necessary to be controlled every millisecond. Maybe it is sufficient like every second or every 10 seconds to just update what the plane is doing. And then there is the outer loop. This is the air traffic control loop. Typically, there are no computers as in the loops below. Typically, there are people in the loop. So the operators see on the radar where is the position of the airplane. They talk over the radio with the pilots and whatever, and they somehow control the air traffic, and then again over the radio give some commands to the pilots to do this and that. And this control loop, this is also a control loop, but this is the slowest control loop. Like every minute or every, I don't know, there is a new command and so on. So, but this is also a real-time system, because if the pilot says Mayday, Mayday, there is some deadline, or there should be some deadline when the operator react, or within which the operators react to the situation and do something. Yeah, so these are different kinds of control systems, and all are real-time systems. Another Another kind of real-time system is a digital signal processing system. So what does that mean? Whenever you have some digital signal, for example, this audio, this is a digital signal. Maybe you have some measurement device. Every microsecond you measure something in some technology and process the signal, do some kind of filtering, whatever. Whenever there is a sampling period, this is a real-time system. For example, every radar system is also a real-time system because you send a beam from the radar and then you receive the reflections, and you need to precisely measure the time, store the reflections in memory, maybe process the reflections, assign whether the reflection corresponds to some plane here or there and which plane it is, and so on. And there is the radar rotates, I don't know, every second or something like that, and within this 1 second you should do all the processing of the reflection, matching of the objects, and so on. So this is another example of the real-time system. Then there are other classes. So for example, there is a special class of databases which is called real-time databases. Again, nowadays, those databases are being merged to like normal databases, but historically they come from industry. If you have a factory, those databases are typically used for monitoring of the production. So every few milliseconds there is a machine which produces some sample, and whenever the sample is produced, the record about that is stored to the database. And once other machines are processing or manufacturing with that product or whatever, some information about what happened is stored into the database. And because the production line goes with certain speed, it is simply required that the database can cope with the steady stream of events like inserts or whatever, and that there are no lags. I have already talked about multimedia, virtual reality, and all these things. These are examples of real-time system. I think you can imagine even more. So that I think that's sufficient as an examples. I hope everybody has some clear view of a real-time system is. And now we can talk about the different classes of real-time systems. I think I will not go into details here, basically very briefly, because we will need this kind of classification in the second half of the term after when we will talk about this theoretical stuff, analysis method, and so on. And depending on which kind of category of real-time systems we have to apply different methods. Yeah, so the simplest kind of real-time system is a system which can be called purely periodic, where everything is periodic, everything repeats every millisecond, and so on. And this is quite simple to analyze and to work with. On the other end of the spectrum are systems which are asynchronous and non-predictable, and this is like difficult for real-time because we don't know what will happen, but somebody still wants us to give some guarantees that whatever happens, we will deliver the result within certain time. And of course, this is very difficult, but unfortunately, this is what people want today. They want basically you to solve many to solve problems which are not predictable, and they want you to solve those problems predictable, which is hard, but well. So in this lecture we will talk mainly about like purely periodic, mostly periodic, and we will also touch like this third part and this wild world of impossible stuff. it's left for you to solve it in practice. We will use a certain terminology throughout this course. So just very briefly, we will talk about tasks, and task is in most cases something which is repeating from time to time periodically. So in most cases, task is composed of jobs, and jobs are executing one after each other. So for example, now we have here video streaming. So the task is video streaming, and job is encoding one video frame and sending it to network. And I don't know, 30 times per second, my video camera and my computer executes this job, grabs the image from the camera, encodes it to some format and sends it to the network, and this is the job. And a few milliseconds later, it does the same. So these will be the jobs. And typically, those jobs have some parameters like release times, deadlines, or relative deadlines, or response times. We will talk more about these parameters later in details, but this is just for you to understand me if I'm talking about tasks and jobs and deadlines and so on. So this is a graphical representation of what I mean by that. Another important distinction in real-time systems is classification of hard real-time systems and soft real-time systems. So hard real-time system is such a system where all deadlines are hard. And what is a hard deadline? Hard deadline is a deadline that has to be met under all circumstances. Typically, maybe it sounds like that dealing with such systems is hard because it's a hard real-time system, but it's not. Typically, those systems are easier to solve because basically whatever is before the hard deadline, it's acceptable, and whatever is behind the deadline, it's not acceptable. So if you are asking, like, is it the system, real-time system, and is it meeting my real-time requirements? The answer is yes or no. It's easy, typically. On the next slide, we will talk about soft real-time systems, and you will see it might not be that easy there. So here we will talk mostly about hard real-time systems because it's a bit easier, at least from like mathematical and analysis point of view. But from time to time, people also need to deal with soft real-time systems. Typical examples of hard real-time systems are like you see nuclear power plant or aircraft control. So maybe if you miss some deadline in nuclear power plant, in case of some critical problem happening there, maybe the power plant will blow up and there's the problem, and that's why it is a hard real-time system. On the other hand, some people claim that no deadline is hard. Even from the laws of physics, in most cases, you can miss your deadline by few time units, like nanosecond or whatever, because and nothing happens. Also, the time is like strange concept. If you look at quantum physics, there are some things which are not very intuitive, and also from that it follows that if you do something a bit later, nothing serious can happen because all the physics is probabilistic. So it is definitely not that if you miss the deadline by 1 nanosecond, things will blow up, and if you are 1 nanosecond earlier, everything is okay. But it's useful concept that simplifies our reasoning about the system. On the other hand, we have those soft real-time systems, and those are systems where all or at least some deadlines are soft, and soft deadline is a deadline which can be missed occasionally. Typical example is multimedia application. Maybe if the network from my computer now is a bit slower, maybe you hear those gaps in the sound. Maybe the video, my picture is a bit jerky. You don't see smooth movement of my hands and so on. But if it is, especially the sound, if it is not like twice per second, it's acceptable. You can miss the deadline, or the computer can miss the deadline, and you accept it. But the question is how do we exactly define like that we occasionally miss the deadline? And that's where things are getting difficult. For example, we can say that 99.5% of deadlines has to be met. Or we can define what's called utility function, like if the result is delivered before or at the deadline, it's like 100% useful. And then if the result is delivered later, the utility goes down, and maybe if we are 1 second behind the deadline, it's useless. And then if you want to analyze such a system, you have to do very difficult math. You calculate, because typically systems are not as simple that there is just one thing and one deadline. Typically there is multiple components, they interact with each other, like grabbing the camera, encoding the image, sending over network, going through the switch, going through the router, blah, blah, blah. Many components is on the way. And all those have those like utilities and probabilities and whatever. And if you want to calculate the final probability and say, I'm guaranteeing that 99% of deadlines will be met, it's very difficult because it's probability and difficult math and so on. So that's the reason why we will deal mostly with hard real-time systems in this course. So, and now another topic, brief introduction to real-time operating system. So why we need real-time operating systems? In most cases, it is needed because the computer is controlling something in real world. So here there is very simple picture of some application which can be controlled, or which computer can control some kind of crane which loads something into the car here, or unloads, and you can control it with the computer. And maybe the car goes left and right, and you have to put some stuff into it, and it's clear that maybe if you open the crane here and the car is not yet here or no longer here, it goes to the right, it won't work very well. You put the stuff to the ground instead of putting it to the car here. So clearly there are some deadlines that such a system has to meet, and those deadlines are given by the physical properties of those systems, like how long does it take for this car to move outside of this area, how long does it take to open this crane or close or whatever, and these kind of parameters. And typically, so you have a computer, and you need to respect those deadlines. And typically, what you do, in the software in your computer, you somehow represent the physical system with some concepts from the software. So, for example, here we have two objects like the crane and the car, and most typically in software, this will be implemented, or the control of those two things will be implemented by two tasks. And those tasks have real-time requirements given by the technology here. So maybe it's some loop, again, control loop, and based on the physical properties of this crane, the period of this control loop is determined by that. The control of the car, the same. There is some kind of control loop or whatever, and it's determined by the physical properties. And so this is what we call like a reflection of the reality in the software system. And we have objects. Those objects interact with each other in reality. And on the software side, this is represented with tasks or with threads or processes or whatever. And then we have some inter-task communication, because those objects interact with each other. Also, those tasks have somehow to interact with each other. And all of this has to happen in real time with proper deadlines and so on, so that this real thing here works. So here we can, I think I have already said most of that. So here you can see what real-time operating systems give us. So they allow us to decompose the control of the system to multiple independent tasks, and to do this reflection in the software. Of course, nowadays almost all operating system support some kind of parallel execution and whatever. But real-time systems, they give some guarantees about the execution, or timing guarantees about the execution of those tasks. Synchronization, of course, we need to synchronize physical systems, so operating system offer us synchronization primitives. Operating systems allow us to like separate the solution to the problem to different tasks. This is like property of all the software, but we should also be able to somehow separate the temporal properties in some way. Operating system, again, not only real-time operating systems, but all operating systems also offer an API, which allow us to use the hardware maybe in a hardware independent way. Also, operating system allow, or especially real-time operating systems, they offer some methods how to efficiently use the resources. So actually every operating system offers those methods, like for example, how to share the CPU between multiple tasks or processes. Every operating system offers that, but real-time operating systems offer a deterministic way of doing that. Non-real-time operating systems may also look like that it's deterministic, but there are typically many cases where it is not deterministic. For example, when the system is somehow overloaded or whatever, it's not deterministic. Operating systems may provide high level of abstractions. I think it's more or less clear. Every software can be written in abstract level. Algorithms for resource management, yeah, that's like the scheduler, but there are also other algorithms like for mutexes and sharing resources between tasks and so on, which are different between real-time operating systems and normal operating systems. And of course, isolation of address spaces. And for real-time systems, some real-time systems offer also temporal isolation. So address space isolation means that one process cannot crash the other process, like my web browser cannot crash my, I don't know, text editor. For real-time systems, we would also like to have something similar, but for temporal properties, like web browser cannot steal execution time from my real-time application, which is not always possible under non-real-time operating systems. So typically, what are the typical requirements of real-time operating systems? Multitasking and multi-threaded. This is like almost every today's operating system offers that. In many cases, we want to have preemptive operating systems. Nowadays, again, most of the operating systems are preemptive, but there are still some operating systems where the preemption is questionable. For example, one of those systems like FreeRTOS, which calls itself a real-time operating system. There are some cases where the preemption is not, it is not possible to preempt everything at any time. And in some cases, it could be problematic. Of course, even real-time operating systems have some parts which are not preemptive, but in case of real-time operating systems, the goal is to limit the amount of those parts and to limit the time when the task cannot be preempted. If you do not understand what I'm saying, I will talk more about that later when we will talk about details of the operating system. So then hopefully you will understand. Real-time basically preemptive means that real-time tasks should not be blocked by other tasks if it is not necessary, for example, because somebody else uses the shared resource. Real-time operating systems should provide a mechanism to prevent priority inversion or to avoid deadlocks. We will talk about such mechanisms later. So we will learn about those mechanisms. We want some kind of deterministic scheduler in such an operating system. So for example, priority-driven scheduler is the most commonly used, but nowadays even EDF, earliest deadline first scheduling, is being used in real-time systems. We want sufficient number of priorities in case of priority-driven system. We would like to have guaranteed response times for interrupt handlers, because typically if you have a computer, the way how the computer reacts to external events is via interrupts. Whenever in the external system something happens, for example, here, if maybe the car touches the touch sensor here, the information that the car touched the point here is sent to the computer via the interrupt. Like there is an event, and we want our computer to react to this interrupt within a certain deadline. And even if our application is perfectly correct and reacts immediately, the problem can be in the operating system. If the operating system is somehow overloaded and postpones the handling of the interrupt to some later time when it is not overloaded, it's not good for a real-time application. So interrupt handling and providing guarantees for interrupt handling is also important property for a real-time operating system. Time resolution, of course, when we talk about time, we must have a way to measure time precisely and to set up timers and so on. Yeah. So those are requirements for real-time operating systems. And last slide about other kind of systems which are also important, but we will not talk much about them. But just I want to mention them because in practice this is quite common, and this is distributed real-time systems. So in case of distributed real-time system, and you can imagine the car, I have already mentioned that there is several, maybe dozens ECUs inside the car which are connected with onboard network and which communicate with each other. Such a system needs to react to external events within the deadlines, but it is not sufficient, for example, that single ECU, like maybe this one, that a single ECU is responding within a deadline. Because if this ECU is a real-time system responding within the deadline, and there is a problem with the network, and there is a problem with another ECU which is receiving the messages and maybe sending and something else to other ECU and so on. So the thing where the temporal requirements can be violated, there are many places where this can happen. And typically what we care about in this kind of distributed system is what's called end-to-end properties or end-to-end deadline. Typically this means I press the brake pedal, the sensor of the brake pedal sends a message over network to braking control unit. The brake control unit computes how to brake each wheel and sends the message to each wheel, and then each wheel has independent brakes. And the control unit there somehow reacts to that message and starts braking with the required force. So as the end user, I only care about when I press the brake pedal, car starts braking. But to do this thing, in case of complex or more complex systems, like with digital systems and networks and so on, there is no single place where this can be handled. So in case of distributed system, we have to deal with the real-time properties of all the components, let's say, along the way. And yeah, this is what people today are solving. In case of automotive, they are inventing like software frameworks, for example, called AutoSAR, how to ensure this, how you can easily validate that all the timings in the car will be maintained and so on. And it's not easy. It's not impossible, but it's not easy. And yeah, technology is evolving, and ensuring proper real-time functionality in this evolving technology is challenging. Yeah, so this is more or less all from the introduction. So now if you have some questions, feel free to ask, and we still have like 9 minutes to the end. So I will use these 9 minutes to start talking about the VxWorks operating systems, which you will meet, the first group of you will meet that after we finish in the lecture. We will meet it at the exercises and start working with that, so that you basically have at least some clue about what VxWorks is. So it seems there are no questions. So let me switch to other slides. Okay. So do you see the slides?
Yes.
Perfect. Raise my screen a bit. Yeah. So VxWorks is a real-time operating system. Typically, this is being abbreviated as RTOS, like real-time operating systems. And today we will look only at some basic properties, but later we will look in more detail about what inside VxWorks, how it differs, for example, from Linux and other operating systems, and so on. So let's start straight with basic properties of VxWorks. We are talking about VxWorks version 6. Nowadays there is a newer version, VxWorks 7, but until I think last year this was not available for the universities, so we are still with VxWorks 6, which is a bit older, but there are no big changes in the system, so it's not really important. So the basic characteristics is that VxWorks is a Unix-like operating system. It inherits a lot of things from Unix systems. The basic philosophy of the operating system is like Unix. So if you are familiar with Linux or FreeBSD or whatever Unix, you will recognize some similar concepts. But on the other hand, it's quite different from Linux. Most notably, it's much simpler than Linux, because if a system has to be reliable, like for sending it to Mars or putting it into the airplanes, it has to be reliable, and it is difficult to make complex things reliable. So VxWorks is quite simple, and maybe for some of you it may look like too simplistic, but remember, this operating system is not here for you to run Facebook or computer games or whatever. It's for controlling airplanes, space rovers, and whatever. So there, the simplicity, in many cases, it is sufficient. So another important property is that the operating system is proprietary. It is being developed by a company called Wind River, which is now a part of Intel. I mean, Intel, the manufacturer of the CPUs. And this is a bit unfortunate, because you cannot just download the VxWorks and run it on your Raspberry Pi or play with it. But for this, you can use Linux or other operating system. Here you have a chance to see something different. That's one thing, and the other thing is, a lot of things that you can learn from VxWorks, you can directly apply them to VxWorks. As you will see, VxWorks offers basically POSIX API, which is the same API as offered by Linux. So, for example, if you program for VxWorks in using the POSIX API, you can just take your applications more or less one-to-one to Linux. On the other hand, if you want, or maybe what's a bit more interesting on VxWorks than on Linux is like how to write device drivers and like low-level hardware stuff, because if you do embedded systems, you quite often need to deal with low-level hardware stuff. And in Linux, you cannot use POSIX API to write like device drivers or low-level hardware stuff. In Linux, inside Linux kernel, you need to use special API offered by the Linux kernel, which is very different from POSIX API. In VxWorks, the system is designed in such a way that both at application level and in the kernel, you can use the same API. So it is quite easy to move your application like between the kernel and the application process, and Yeah, and you don't need to learn a new API for that. So of course there are other advantages and disadvantages. We will touch those like as time will go. So under VxWorks you have by now it's pretty common, like unlimited number of tasks running there, preemptive scheduling, priority based 256 priority levels, fast and flexible inter-process communication. Nowadays it's common, but when the VxWorks were a new operating system, which was like in 80s, 90s in last century, which is quite long time, it was not that common, and it was even not that common because some people say that the name is inherited from the fact that there were some operating system VX something that simply didn't work well, and so they developed a new operating system and give name VxWorks so that it works correctly. The operating system supports all the things that you are used to from other operating system, like your slow-level communication primitives and so on. So if you had some operating systems course, you are probably familiar with that. And by the way, maybe I have a question to you. If you can raise your hand, if you had operating system course either with me in bachelor or yeah, so raise your hand if you had some kind of operating system introduction or whatever. I guess that mostly people from Open Informatics had that. Yes, so it's like good. So if you can put down your head, I don't know how to, whether I can do it myself. And now, are there some people who are having operating system course in this semester? Good. One or not, I don't know. Okay, yeah, so good. So maybe because the people having the operating system course, it's a minority. It's like 15 people from 60. I will be repeating maybe some basic concepts from time to time. So for those who already know that, I apologize. On the other hand, if I am talking about something and the people from cybernetics and robotics do not have clue about what I'm talking about, just let me know and I will explain what's going on. Yeah, so time is over. We finished at least a brief introduction to VxWorks. Thank you for your attention. We will continue next week at the same time, and we will start first lab in 15 minutes. So the labs will be according to the schedule. The thing is that we cannot do like all the labs at the same time, because we have, unfortunately, VxWorks is a proprietary operating system, so we have limited number of licenses, and we cannot like put all of you at the same time to use the to get access to the system. So we have to split it to multiple classes. Okay, so if there are no any questions, so feel free to leave. It's everything from my side today. If there are any questions, just you have few minutes to ask now.
Zeptám se česky. Mohl bych se zeptat, jak se dá zaručit nějaký real-time třeba u cloud gamingu, kde to řeší, kde se snaží dělat ty real-time na naprosto ne-real-timeových systémech, aby byla dostatečná odezva?
No to se řeší tak, že například když posíláte pakety na síť, tak tam nastavujete správný flagy těm paketům a doufáte, že většina switchů a routerů po cestě ty flagy nebude ignorovat a dá těm paketům prioritu před ostatníma paketama. Stejně tak ten server je tam naprogramovaný jako prostě real-timeová aplikace, když přijde nějaká zpráva, tak se tam někde nezasekává, hnedka tu zprávu nějak zpracuje, aby se nezablokoval a posílá zpátky odpověď a tak. Ale samozřejmě jako není to 100%. Stačí to takhle?
Jo.
Tak ještě nějaké další otázky?
To budou všechny cvičení v angličtině?
Ne, cvičení v angličtině, myslím, jenom je to poslední čtvrteční cvičení, ale přiznám se teďka, že úplně si nejsem jistý, protože oni v tom rozvrhu s těma cizincema nám dělali dost zmatky, že tam nějak zapisovali ty studenty prostě kam se jim zlíbilo, takže si nejsem úplně jistý, jak to nakonec teďka dopadlo. Naším cílem je mít jakoby jedno cvičení v angličtině, ale může se stát, že na nějakém cvičení budou studenti namixovaní, tak tam to pak bude, že třeba nějaký úvodní povídání bude buď to v angličtině a pak jako je většinou to pokračuje, že prostě si povídáme se studenty a to pak si budeme povídat tou řečí, jakou student bude chtít, takže to bude v češtině.
Dobře. Takže poslední cvičení ve čtvrtek je záruka, že to bude v angličtině.
No, tak úplně hlavu na špalek bych za to nedal, ještě se tam musím teďka podívat, ale takhle jsem se domluval, takhle jsem to psal rozvrhářům, ať všechny cizince dají do toho posledního, jestli to tak udělali, to jsem, přiznám se, neskontroloval, jo.
Dobře, díky.
A pokud mám ten předmět zapsaný jakoby v angličtině, ale cvičení mám hnedka, co teďka následuje, tak bude mi uznaný jako anglicky, nebo jak to funguje tohle?
Já myslím, že jo, tak vy budete na přednáškách budete anglicky, na cvičení se s váma můžu bavit česky, ale pokud budete chtít, tak se taky můžeme bavit anglicky.
Dobře, děkuji.
Ale myslím si, že to pro to absolvování předmětu jako není potřeba, abyste i to cvičení měl v angličtině.
Díky.
Tak, ještě někdo má nějakou otázku? Tak zdá se, že ne, tak já tady možná vypínám teďka nahrávání. Jde to? Takhle. Tak a jestli chce někdo ještě položit otázku mimo nahrávku, tak taky může teďka.